Okay, welcome to Information Theory Lecture 34, and you may have noticed that we've got a new title page. A new title page which has a number of significant features, one of which is that we've got a little picture down at the bottom. So if you're wondering who caused all of this, there he is, Shannon himself, although it looks very blurry. There he is, now he's much clearer. So we've got a little icon picture. And secondly, in case you're looking for the lecture number, it's right there now. Okay. Now, why is this done? It's in order to fix this business down here. You've probably seen that mess up a couple of times in previous lectures, near the ends of the lectures. But that won't happen anymore because everything is now fixed. So this is lecture 34. We have only 3 more lectures in the class. So today we're going to talk about network information theory and the multiple access channel and a number of its guises. And then we have 2 more lectures next week on network information theory, and then including some very modern aspects, which we will be doing next Thursday. Most of today's material is drawn from chapter 15 in our book, although I do suggest, like I've said, to read the corresponding chapter in Jung's book, because we'll be drawing from that next week, so you can get a step up or a little bit ahead by reading that, in addition to all this other reading that you're doing in reading each other's papers. So I'm not even going to say that. Here's again information on the final projects, which I've already gone through. We have the next deadline for the final project is Monday, March 10th. And it's another updated write-up on what you've been doing, status update. The next slide summarizes all of the remaining assignments that you have. Just to remind you, so this Friday at 5 p.m., everybody has 3 one-page summaries of the papers that you were assigned to read, uploaded to our, whatever it's called, Dropbox or something. And once done, I will then resort them and assign them to the primary reviewers of the paper to actually grade by the following Tuesday. Well, then we got this deadline, which is the final project status update, and then on Tuesday, you have a grading due. And then your second round of assigned papers are due a week from Friday, March 14th. I don't know, this is pretty obvious, I hope. And then we have our 4 slides, final slides in 4-page paper due Monday, March 17th at 1 p.m. electronically. Someone asked if they can actually use like some subset of the pages of the 4-page paper for your status write-ups. You can do that, but you have to keep it at 1 page. So you can't like upload 2 pages and then the next week upload 3 pages. Each one of these status reports are supposed to be 1 page. And like I've said before, I've never, ever taught a class where I've asked for 1-page assignments and everybody has successfully only given me 1 page. There's always been at least one person, usually more than one person, who gives me more than 1 page. Now so far this class is doing well. I'm really surprised. However, there's still time to break your record. So if you break your record, and if one of you is the person, I will publicly embarrass you by putting your name out on YouTube for the rest of eternity and saying who it is. So otherwise, those of you who abide by the rules will remain anonymous, safely anonymous. Final presentations are March 17th, 2:30 p.m. In this room, and then finally, our last assignment for the quarter is March 18th at 11:45 p.m., which is the final grades. Okay. All the assignments are there, so you don't have to wait until March 18th. I'm not fascist in the sense like I open the web page up at March 18th in the morning or anything like that. So you can do them early if you want. Okay, so a bit of review. I mean, in some sense, we don't need really to review this stuff for today's lecture, but I added it in because I think it's worthwhile. We defined this general notion of an information inequality, which is basically a weighted sum of entropies where the weights, it's entropies of groups of random variables where the weights can be positive or negative. And any information inequality might or would take this particular form. These are obviously linear inequalities. You can imagine other types of inequalities, but we're primarily interested in the linear inequalities. And interestingly enough, we discovered that the Shannon implications, the non-negativity of the conditional mutual information, which was known early on in information theory, is not sufficient to define the class of entropy functions, in that, as late as 1998 and 99, people discovered other inequalities that were true of entropy functions, but were not true of polymatroid functions. And here are some of them, but there are lots more. The nice thing about these are that these are explicated, although we know that there are more, but we don't know them. We just know that they exist. Here's one that is actually true of polymatroid functions, and so therefore true of entropy. This defines a very, very large and interesting class of inequalities, which you can use to derive a lot of other inequalities, because these are parameterized by sets of C. And then the other thing we talked about was other forms of entropy, or other forms of like information function derived from sets of probability values. And one way to do that is to generalize the notion of an aggregation function, phi. And we saw that if we take this phi, if we take the identity aggregation function in this equation, we get back the regular entropy function, which has this additivity property, namely that the information of independent events adds. It adds into two chunks, this chunk and this chunk. And the question was, are there any other phi functions? And the Rényi entropy is one that says, yes, there is another phi function. Here's one. And when we plug that in and simplify and do everything, we get the Rényi entropy, which is probably the most famous of the information-like functions and probability distributions, other than the regular Shannon entropy. We have some bounds. We also have that it generalizes regular entropy. So in some sense, this is a very entropy is just a member of this much larger class of entropy functions. And what's interesting is that you can plot this. Like I would suggest, and this isn't an assignment, but if you're interested in this, go to MATLAB and look at the binary function and plot what does the binary entropy look like for these different values of alpha. And as I said last time, if the binary entropy function sort of looks like this, it's kind of not very sort of roundish shaped. These other ones might look a little bit more square, or maybe a little bit more thinner at the top. So if you want to be more concentrated, where you're saying maximum information is concentrated at the 0.5, or you want to be less concentrated, you can control that in some sense concentration degree by the parameter alpha. So alpha could be in some sense seen as like a form of controlling concentration. Concentration of where the maximum value is. And that, like I said, that could potentially have some applications. Okay, so this is a slide actually that comes from from lecture 13, I believe, from last quarter. And I just wanted to remind everybody, because in talking about network information theory, we're again talking about channel capacity. We're generalizing the notion of channel capacity. And remember, the channel capacity was defined as the supremum of all achievable rates. And so remember, an achievable rate was one that was such that there exists a sequence of 2 to the n codes that have vanishingly small probability of error as n goes to infinity. So in other words, that rate, and the rate corresponds to the number of bits per channel use, is achievable because it means we can make the block length big enough, and the error will go to 0 very fast. And then we define this sort of information capacity, which is this optimization problem, and we found out that this was the limit. This was the critical point at which all rates below this capacity were achievable, meaning that as the block length gets big, the probability goes to zero. And if you're above the capacity, it's not achievable. And we saw these kinds of plots where we can look either on the right-hand side at the error exponent, or we can look at the log of the probability of error. And the error exponent is positive, meaning that the error is e to the negative arrow exponent. So as long as the error exponent is positive, the error is going to go to 0 exponentially fast. But as soon as the error exponent becomes 0, which happens at this point, then the error is not going to go to 0. So notice that the only constraint, the thing that we're doing now is we're generalizing this to multiple dimensions, right? So right now we have one axis, which is just the rate. And the rate is either less than c, equal to c, or greater than c. Right? So you can think of this as a very simple polytope. Right? It's a polytope in one dimension, which corresponds to this region right here. That's the achievable region in some sense. Right? Those are the rates that are such that you can achieve a code with vanishingly small probability of error. But now in the case of network information theory, we have lots of senders and lots of receivers. Right? And you can think of this as points on a network. And these points can be all sorts of interesting things. They can be computational engines, and so they can do recoding. They can do they can be active or they can be passive or anything in between. They can have bounds on the amount of computation that they can do. And we're interested in this vector of n squared rates. So it's in some sense, in this most general case, you can think of it as we're in r to the n squared. And any given point in this space r to the n, because it's m squared, we're using m here, r to the m squared. And any point, any set of rates might be such that, yes, we can show that there exists a sequence of code such that as the block length goes to infinity, the error goes to 0, where the error means that everybody gets to communicate error-free. Or a given point in r to the m squared might not be achievable, meaning that one or more pathways from one sender to one receiver might be such that its error, that can't be achieved, that point can't be achieved. And again, that doesn't necessarily mean that you're communicating directly from A to B. You might be communicating partly from A to B, partly from A to B through C, and partly from everywhere to everywhere else. It really depends on the specific setting. And this most general setting is very, very general, right? But this is the quest, is to come up with a universal theory of achievability for a general network. And this is a quest that is not yet realized. So we don't have an equivalent understanding in the network information theory case as we do in the Shannon case, in the single point-to-point communication case, where we know precisely this point. Right? What would be equivalent in the network information theory case? It would be having a complete characterization of all points in r to the m squared that are achievable, and what is the boundary between the achievability region and the non-achievable region. What instead we have in this general case are, in fact, not even in the general case, in very specific cases, sometimes we can actually characterize the region, as you will see in the MAC case. That's one simple case where we can. But in other cases, we might have inner bounds. We might say, well, I know here's some region and some convex hull of this region or something can be achieved, but I don't know if that's tight, or I know that that's not tight. I know that there exist other points outside of this region that are also achievable, but I haven't been able to characterize that. Other cases, you might have an outer bound. You might have a superset of the region, or you might have some intersection partly with the region. So it's still a research topic, and a lot of what people still talk about today in information theory are trying to increase the inner bounds and decrease the outer bounds, and generalize the settings. So the first instance that we're going to see, the MAC channel, so that's basically what this is saying. It's like saying, okay, well, now we've got, one way of characterizing this would be to say, for all subsets of V, so V is a set of sources, and for all subsets S, we have this capacity function, which says that the sums of the rates inside of the set S can't exceed that capacity, that specific capacity. And this would be a polyhedral type of constraint. But must the achievable region be polyhedral? Yes? No? Is this the most general? No.
Linear combination of the rates, right?
Yeah, no, it's not necessarily most general. So this is one possible thing we might want. We might have a polytope associated with this, but maybe the region, the set of achievable rates, might take a very different form. Might it be non-convex? Like this, in this particular case, it's a convex region. It's a polyhedral convex region. maybe it's not convex, maybe it is convex, maybe it's continuous convex, maybe it's not polyhedral. So this is one possible type of generalization in the polyhedral case. This directly generalizes the one-dimensional case, because when v is equal to 1, we get back to one-dimensional case. But it's not necessarily the case that the set of constraints exactly has this form. So that's important. So in fact, maybe, since it's important, I should change this word to might. We might want. And then ask the question, is this most general? And the answer is no. We don't know, or we're not sure. Or maybe we're not sure. All we need to do to answer that question is, if it's most general, is find an instance where this one doesn't work. So again, what we mean by not work is to say that this set of rates, we need to say, take the set of, the union of all rates that are achievable. And if the union of all rates that are achievable can be described by this convex polyhedral form, then this works. Otherwise, if it's not convex or if it's not polyhedral, then this form doesn't work. But you can see right away how this is a generalization of the one-dimensional case. Right? These kinds of problems, the polyhedral versus non-polyhedral, doesn't really come up in the one-dimensional case. Okay, so now the first set of tools that we're going to use to solve these things are basically, and this was a very natural approach given what Shannon did, is to sort of generalize Shannon's approach. Say, okay, well, we've got typicality theory, we got the weak law of large numbers, we define a typical set, and which is what we're going to use, and we're going to use that to analyze the MAC case, multiple access channel. The only thing that, like I said last time, is maybe something important to realize about this is that we're defining typicality means for set of S. So S is the set of indices of random variables. We are requiring it to be typical for all subsets of S. So keep in mind that bit over there.
Question.
Yep.
So for the multiple access channel, they're all trying to communicate to one guy.
Yeah.
Who's not in S, or who could be in S. Or...
Who's not in S?
Okay.
That's right.
And so in this general case, they're trying to communicate to just anybody who's not in S.
Well, I mean, to be honest, actually, we are going to be, since we're going to be talking about joint typicality, when we specialize the notion of typicality to these different channels, why, the receiver is going to be in S, in V as well. So, I mean, in this particular case, we're just defining, we just have a set V here. And in general, V can include the receiver too. Because remember, even in the directed point-to-point case, we needed to talk about joint typicality, XY typicality. So here, this is just this general notion of typicality where we've got a set of indices, V, and we have some subset. So I guess, to answer your question, is it in S? It might be.
Okay.
Y might be in S. I mean, so Y might, more specifically, Y might be in V, and S is a subset of V, so therefore, Y might be in S. Okay. But here, I guess we're sort of collapsing. We're just naming all variables X for the sake of simplicity. But in general, we'll just rename it. I mean, there's an asymmetry because Y is the ultimate destination. So these theorems we're just going to use. I'm not going to prove them in class like I said last time, but I hope everybody remembers them. I'll probably do. I'll just do this and say, remember that the size is equal to this 2 to the entropy or something, right? Like here, or maybe if this if we're jointly typical. S1, S2 typical, then the conditional probability can be represented, up to first order of the exponent is 2 to the negative n, the conditional entropy of x1 given x2. Okay. There's a lot of notation to sort of, I'm not even going to say all of this stuff, but hopefully this is intuitive and clear, and we'll just take these as a given. The other one that, of course, we need is this one, this upper bound on the size. In this case, it's the conditional size. And we have this lower bound as well. where we're taking the expected value, the size. And then this is the other one that's a little bit different than what we saw before. What we saw this last time is that when we have a set of random variables that are sort of governed by a Markov chain, or equivalently conditionally independent. So given S3, S1 and S2 are independent. So this is the same kind of thing, because remember when we proved the converse of the channel coding theorem, we said, oh, well, one thing, we did this symmetrizing argument, which was Shannon's brilliant argument that said we can just, without loss of generality, assume that the index the message that's being sent is 1. And so one possibility is that when we send message 1, that the code word for 1 and y is not jointly typical, so that goes to 0. Another possible thing, since the codes are generated independently, is that some other code word in y is jointly typical. So that's the case when things are independent and jointly typical. We want to bound the probability of that, and that goes to 0 as well. Here, this is a generalization, as we're going to see in the network information theory case, is that in the case when S1 and S2 are independent given S3, that's going to correspond to one of the cases that we're going to have to analyze when we use the union bound, as we will see. And what that says is that when we have that stuff that's generated according to a conditional independence, which corresponds to that analogous situation which I just described, we've got that the probability is 2 to the negative n, the mutual information, the conditional mutual information. Right? Which kind of makes sense, because it's saying that if things are drawn independently, conditionally independently, I should say, and they're not, then that probability is going to go to 0. That typicality, that event, drawing things conditionally independently when they're not, is going to eventually be impossible, or as improbable as you want it to be, exponentially fast. Whereas when things are truly conditionally independent, and you draw them conditionally independently, then nothing is driving it to 0, because in that case the mutual information is 0. So everybody get what we're saying? So here's the multiple access channel. You got 2 senders and 1 receiver. The idea is that, again, W1 is a sender, W2 is a sender. These guys can't talk to each other. So these guys are separate, independent. We get back a Y, and from Y we need to somehow recover both messages. And we talked about some examples of communicating to New York from Seattle and San Francisco simultaneously, where we interfere with each other. And this is sort of clearly an upper bound. If we were to maximize over this joint distribution of the mutual information, so if we were to do something like, let me make sure this is clear. I wasn't sure this was clear last time, but if we were to do max over P of x1 and P of x2 of mutual information between x1, x2, that wouldn't be a valid, that wouldn't be valid, because that basically requires us to cooperate, x1 and x2 to cooperate. It means that x1 and x2 need to communicate with each other. They need to be correlated. We're not really allowed to do that. What we're sort of doing is we want to understand the communications capacity. We might want to do something instead like we maximize over the product distribution here, where this guy here is a product distribution. But it's in fact a little bit more than that, as we are seeing, as we're going to study. The notion of TDMA, time division multiple access, is not something we're going to formally define, but we're going to it basically means time sharing, where senders can sort of agree, okay, you do this first second, if everybody's synchronized in a clock, and I guess the idea is that you don't really need to communicate if you're synchronized. You just coordinate through timing. And that's sort of a very simple way that, once you do one bit of communication at the beginning to synchronize, then you don't need to communicate thereafter if you have accurate clocks. And so you can do time sharing. Like, okay, you go first, and you go 1 time unit, and I'll go 2 time units, and you go 1 time unit. So you can say, I'll get 2/3 of the time slots, and you get 1/3 of the time slot. And you can agree upon that beforehand. And that's a very, very simple way, if you have synchronous clocks, of achieving other rates. Very simply. It's not necessarily the best way. Again, without getting into the specifics of coding theory literature and the real hardware implementations of these things and software implementations of these things, one should at least intuitively have a notion of what TDMA is. Because it will allow us to do other things if we're willing to just assume it in this loose form. Okay, any questions about the review? Okay, so we already said this. So basically, the two senders can't communicate to each other. This is just a bunch of definitions. We sort of stopped last lecture halfway through this slide. So a discrete memoryless multi-access channel, so it's memoryless in the sense that each time, there's no, we use blocks, but there's no memory between channel uses. We've got an alphabet, x1 and, the two sources have an alphabet, which is x1 and x2, and the receiver has an alphabet, and we have this probability distribution, P of y given x1 and x2, which models our channel. So our channel the channels are not independent. Right? Or in other words, I should say it is one channel, really. So what x1 does can greatly influence what happens to x2 when we try to communicate to y. That's what makes it interesting. What would happen? What would happen if the channels, if the pathway from x1 to y and x2 to y were completely independent? What would happen in that case?
Parallel channel?
Yeah, what would be the rate? What would be the capacity? What would be the limits on the capacity? The limits on the rate, I mean.
Just be the sum of the two.
Be the sum of the two capacities, right? Because there's no interference. So it's a very simple. We have an example of that, even. Here's the definition of a code for math. It's a 2 to the nr1 to the nr2, and code is so basically it's a sequence of codes, really. It's a function of n, where we've got a set of messages, W1 and W2, and we have 2 to the nri possible messages, because that's the thing that can be encoded in nri bits, just like we saw in channel communication. And we have an encoder function, which basically takes a message index and comes back with a code word, and another code word. So we have two encoders, x1 and x2. So we turn an integer into a length n string of input source symbols, or input channel symbols. And then the decoder, what the decoder does is, it takes a sequence of output symbols from the channel, y of n, so everything's length n, and it comes back with two messages. The one corresponding to W1. So again, these things the messages can be intertwined, but what you map into is a pair of integers rather than just a single integer. Because you want to be able to distinguish between who sent what. Without loss of generality, we can assume that the source messages are uniform and independent. That doesn't really hurt us. And in general, that just means that you're being efficient about which messages that you send. Remember, we can always do entropy compression at the source. We already have independence. And if you have entropy compression, then every bit is uniformly probable. We've done ideal entropy compression, so that just means we're being efficient in our use of messages. That the rates are not higher than they need to be. And we have a definition of the probability of error. And what this says is that given that we've sent W1 and W2, what's the probability that we've decoded something other than W1 and W2? And then we're taking the probability, we're summing that probability over all possible combinations of message sends. So that means that there's 2 to the n R1 plus R2 possible terms in the sum. And we're just taking the uniform average. Okay. Everybody with me? So we have a notion of achievability, and I think conceptually this is very similar. This is a generalization of what we've already done. We have the pair is achievable if there exists a sequence of such codes where that probability of error goes to 0 and n gets big. Okay. And then the capacity of the region is the set of achievable R1 and R2 pairs. So right now we're in a two-dimensional space, right? So we can, for example, make a plot where we have R1 and R2, and maybe we've got this funky green region where it's achievable, because it's never negative, so let me just do it. Like this is achievable, everybody's happy, that's something that we can do. Any pair within that region is such that we can do it, but anything outside this region is unachievable. right? It's not possible. There's going to be a guaranteed error somewhere outside of there. Okay. So that might be, we might see. But then the question is, we want to characterize this boundary, whatever that is. Is it convex? Is it not convex? Is it polyhedral? Is it not polyhedral? Now, here's the theorem that characterizes it for the MAC channel. The MAC capacity, that region in which I just wrote, is the closure of the convex hull of all pairs R1 and R2 satisfying the following set of inequalities. So first of all, let's forget about this closure of the convex hull for a minute, okay? Just to understand this theorem. Okay, so we're saying that R1 and R2 is achievable if it satisfies this inequality, meaning that R1 sort of individually has to be less than the mutual information between x1 and y1 given x2. R2 has to be less than or equal to that corresponding mutual information, x2 and y given x1. And then together, the sum of the rates can't exceed that third inequality. Now that third inequality kind of makes sense because that's the bound that we would get if x1 and x2 were allowed to communicate, right? So if x1 and x2 were allowed to communicate, there'd be no way of communicating more than the max over the joint distribution px1 and px2 of that quantity. Okay, but that's just mutual information. How do we get the max? Okay, where does the max come in? So certainly, like in the case of the regular channel capacity, we computed the max, right? And as soon as we got the max, as soon as we got the capacity C, which is equal to the max over px of the mutual information between x and y, we know we can always communicate less than the capacity, right? You can always add noise. I mean, that's easy to do. Here, the question is where is that max? So in some sense, what we're saying is it's all possible pairs of R1 and R2 that satisfy this. And that's equivalent, if it's in the one-dimensional case, it would be equivalent to saying it's all rates such that the rate is less than or equal to the mutual information between x and y for some p of x. That would characterize the achievable region in the one-dimensional case too, right? So what we're saying here is on the one hand, we're saying the same thing differently in 2 dimensions, because we're not taking, what does it mean to even take the max? Because we need to sort of talk about, when you're talking about max really only makes sense when you're talking about one-dimensional scalar quantity. When you're talking about a multidimensional quantity, you need to get into sort of Pareto optimality. You need to talk about a region where if you increase one, you have to decrease the other. That's the notion of Pareto optimality, the Pareto frontier, as it's sometimes called. And that, so like that frontier would correspond to like this boundary. If you maybe increase one, you have to decrease the other, right? You can't. That's what sort of in some sense the definition of Pareto optimal means. It's a whole boundary. So on the one hand, we're sort of characterizing this based on this sort of frontier, or this boundary type method, and we're saying it's the union of all rates, so it's all possible rates that satisfy that. And then the last thing we're saying that's different is that we're taking the convex hull of all such points. So it means that if we got this point here, we got this rate pair here and this rate pair here, we can take any convex combination of the two rates. So any on the line between R1 and R2 of the two pairs of R1 and R2, we can also achieve that. Okay, so while this looks like it might potentially be polyhedral, as soon as we take the convex hull, we're probably going to lose polyhedrality. And the other thing that's really important about this statement is that this is under a given product distribution, right? So remember, so when we instantiate a given product distribution, we sort of implicitly have we implicitly define these quantities here, right? And we're saying, okay, well the rates have to be less than that. And then you instantiate another product distribution, and the rates have to be less than that, and so on and so forth. And you have all of these different things, this has to be true, this has to be true, this has to be true. In the one-dimensional case, it's sufficient to just say the max over P of X of that thing. Then all these other inequalities are satisfied. Because we're taking the union of all achievable rates. But here what we're doing is we're sort of like, we're measuring this in a different way by just saying that this is true for a given product distribution, and then we're taking the closure of the convex hull of all of these things. Is that clear? Should I, one thing, I mean, if it's not clear, what I could do is I could go back and do the one-dimensional case using this kind of language. I mean, let's do that, okay, just really quickly. Let me see if I can do this. If I can duplicate a page. There's some way of duplicating a page. In which case, I know there's a print. I'll forget it. I'm just going to draw on this. And I think I've just crashed this program. What I'm going to do is the following. So I'm just going to erase this stuff, since this is on video. So let's just do this for the one-dimensional case. I'm just going to cross stuff off that doesn't matter. So it's not a map. This is just a one-dimensional case. We just have R, and none of this stuff is going to matter. And this is just x2 doesn't exist, and we just have x1. And we just have one distribution. So if we said that, do people see how that's exactly the one-dimensional case? Capacity of a channel is the closure of the convex hull of all rates satisfying, it's just rate. It's just the rates less than the mutual information under a given distribution. There we go. There's the one-dimensional case. So the question?
Well, so your comment on, in the two-dimensional case, then it's not a polytope. Like you're saying that, well, it's a convex hull, so you can have curved sides. For
yes.
Okay.
Yes. In the one-dimensional case, it doesn't matter, right? So it's like the convex hull stuff. I mean, this means that it's a continuous region. Right? It means that there's no gaps.
So,
but it doesn't change the shape. It doesn't mean that there's a curve in one dimension.
could you remind me why we were talking about polytopes a couple slides ago?
Because it's important to understand the achievable region, because we're saying each one of these, for each product distribution, we're defining a polytope. So this is so let's unerase. Is everybody happy with the one-dimensional case? And let's unerase this guy. Go back to the two-dimensional case. I really have to learn how to duplicate slides on the fly. We go back to the two-dimensional case, and we see that for any particular pair of distributions, we do have a polyhedral description of the rate, of the restrictions on the rates. But we're taking the convex hull of all these restrictions. So it's kind of like taking the union of a bunch of polytopes, or polyhedral regions.
So if you just sample that at a bunch of x's, and so you have finitely many points.
A bunch of p of x's.
A bunch of p of x's, then it'll still be, the convex closure will still be a polytope.
Yes. Yes. But since p of x, px1, px2 is an uncountable set, then it's curved. But we're going to look at these and analyze what each one of these polytopes look like, and then we're going to look at its closure. So for a particular pair, this defines a polytope. In fact, in 2 dimensions, it's sufficient to call it a pentagon, which is the junior high school name for a polytope, right? A 5-sided polytope. And that's going to be an R2, and the reason why that's true is because we have this set of inequalities. Right? So the max of this is less than or equal to this, which is less than or equal to the sum of the mutual informations. And that basically, that right-hand side follows because, again, x1 and x2 are presumed independent. And here's what it looks like. So what we have is, on the one hand, we've got sort of the unary constraints on R1 here, and the unary constraint on R2. At some point, if we increase, if R1 keeps increasing, then that's going to start decreasing the requirement on R2. And in which case, at some point, R1 is going to reach its limit, and then we can always do this. And anything inside of here, of course, it seems perfectly reasonable that the region is going to be down closed. And it always is going to be down closed, because if you actually have, if you find a point is achievable there, say, you can always get this and that, right? Because you can always add noise to your signal and decrease your rate. So it's down closed, or subclusive, as it's sometimes called. And it looks like that. Now, one thing you might be wondering is, why have I labeled this, this, and this? I will talk about that after we prove the theorem. But just keep in mind that these points here, point at these vertices, are just the mutual informations. There's a nice intuition for why that is. Okay, but that is a polytope, and any pair of rates within this polytope is achievable. But that's not the whole region, right? That's not what the theorem is saying. It's saying that that's one polytope. So let's see if we can, just by looking at this for one particular, for this set of equations, see if we can characterize that. Is there something nice about that polytope? So if we look at that, you know, we have the mutual information between x1 and y given x2, and mutual information between x2 and y given x1. We can sort of think of x1 as x1, x2 minus x2, right? So what ends up sitting here is sort of like, in some sense, you can think of it as like the complement of x2. Like this is the complement. This is like x1 complement. This is like x2 complement. So let's generalize that for a minute. And just talk about indexes of sets of random variables and look at the mutual information. And when we expand out the mutual information, in this most general case, so we're using this form, this sums and differences, this inclusion-exclusion formula for mutual information, we can expand that out for this form where we have S, the mutual information between S, Y, and V except for S, which is S complement. We get this particular form. Right? So we're saying things like, for example, the rate is less than or equal to I of S, Y, given V except for S. So those are the kinds of things we're saying. And the question is, does this basically mean that the polytope looks particularly nice or has some particular property? It doesn't, but on the other hand, it turns out that for the multiple access channel, and we're talking about two sources, but in general, in the multiple access channel, all of the x's are independent. And thanks to the independent, it turns out that this function of the set of indices, is a submodular function. And so basically it means that there's this notion of there's a particularly nice polytope called a polymatroid. And this is, it turns out that each one of these polytopes is polymatroidal in shape. Which has all sorts of implications, which if you're interested, I again suggest you take my submodular class next quarter. But the bottom line here, however, is that under the MAC assumption, each one of these polytopes is polymatroidal, which is nice. Now what we want to do, however, is come up and characterize the region more generally. And so therefore so that we can actually find these capacity constraints in this convex closure case and prove the theorem in general. So before we do that, let's do a couple of examples, some extreme examples. You had a question last time about whether or not, can't we just put a bound on the sums of the rates? So in other words, why isn't it the case that we can just say R1 plus R2 is less than some constant and be done with it? So you'll see in a minute, but let's take a break and then come back and do these examples. So here we are back after break, and let's do a simple example where we have And this was the example I raised a little bit earlier, where we have two completely independent binary symmetric channels. X1 to x1 to y1 and x2 to y2. And there's no interference between the channels. And so the idea is that y is like this vector valued signal that we receive. So y is just basically something that, from which we can pull out y1 or y2 very easily. You can always encode two integers within an integer as long as the integers are bounded, right? And so each BSC then has a rate, and we know what the rates are. The rates, these are binary channels, and so the rates are equal to 1 minus the entropy of the corresponding source distribution, right? 1 minus pi. And so what's achievable in this particular case is this square. So we know that, for example, the first channel can't communicate more greater than this rate down here, which is just C1. And the second channel, or it's really the same channel, we're assuming it's the same channel, it's just that these things don't interfere with each other, these don't interact. So the second part can communicate at a rate of C2. And so all of these rates, as long as each one of these individual rates are less than the corresponding capacities, are achievable. And so our our achievable region is just this square. Right? And the convex closure doesn't really do anything, does it? So that's an example of what you said, right? So it's just the rate sums. Okay. But on the other hand, we might have a very different setting. Let's have a channel that has massive amounts of interference, a binary multiplier channel. Okay, so y is equal to x1 times x2, and these are still binaries. And we're trying to communicate from x1 and x2 to y simultaneously. Okay? And y is binary. So if x1 is equal to 1 identically, and this is equal to 1. So remember, x1 and x2 are independent. If it was the case that the probability distribution of x1 that's such that x1 was equal to 1, then x2 can send to y perfectly, right? And so the rate is basically just the rate at 2 is equal to 1. So we have a point where r2 is equal to 1 and r1 is equal to 0. So that point is achievable in this channel. Right? And then similarly, if x2 is equal to 1, so the probability distribution over x2 is such that the probability of x2 is equal to 1 is equal to 1, then that basically means that x2's rate is 0, while x1's rate is equal to 1, which is this bit here. And so that's an achievable pair. So we have two achievable pairs. The first achievable pair is this, and the next achievable pair is this and this. And so we can plot this. Oh, there was one more bit. We know that the max achievable rate on both of them is the max over y. The max of the mutual information of x, this is under any case, even if they were allowed to communicate, would be 1, right? Because y is a binary variable. So we know that the sums of the two rates can't exceed 1. That's an upper bound. So we have that bit of information, and we can write this. So we have this point here. This is the first point, this is the second point, and then the sum allows this. And so the polytope is triangle shape, and that's exactly it. So again, the convex closure doesn't really change anything. How would we very simply achieve a given point, say here? How would we achieve that point? So we know that if we can achieve there, we can do anything below it, right? But how do we achieve a point on the boundary? A very simple strategy would be, again, to use TDMA. Right? We would just use, let's say that that's 1/3. Say this is 2/3. And this is 1/3. So we just divide time units into, and one guy, I guess R2 would get 2 time steps for every 1 time step that R1 gets. And then just by dividing time into sort of corresponding fractional units, you can essentially achieve any point you want. Again, this requires a synchronous clock, but that's you know, you might think that that's a little bit of cheating, but maybe it's not. Maybe it's realizable. Because it does involve coordination, but it doesn't really involve communication. So everybody see that? Okay. So let's talk about the binary erasure channel. So you remember the binary erasure channel from lecture 13 last quarter? This is just review. These slides are from lecture 13. So the binary erasure channel is one where x is binary, y is ternary, and what happens is that every time we want to send a bit from x, it's possible for it to erase. It gets the symbol e. And the idea is that if y gets a 0, we know that a 0 was sent. If y gets a 1, we know that a 1 was sent. If y gets an e, we don't know. It could be either 0 or 1. Right? We don't know what it is. And we know that the entropy is upper bounded by log 3. Does anybody remember the capacity of this channel? There's a very intuitive definition of the capacity. So if alpha was equal to 0, what would be the capacity? 1. And so what we're doing is we're throwing away alpha % of the bits, right? So because as soon as we get an e, we just have to toss it. We don't know what to do. And it's symmetric. So what's the capacity? 1 minus alpha, exactly. So I'm not going to derive it again, but here's the capacity. Okay, so now what we're going to do is we're going to use the binary erasure channel capacity to sort of analyze this thing called the binary erasure MAC. It's not exactly a MAC because remember it's not exactly a binary erasure channel because it's a multiple axis channel, but we're going to use it to analyze this. So in this particular case, the channel is basically y is equal to x1 plus x2. Okay, where the alphabet size of x1 and x2 are binary, and the alphabet size of the output is ternary, again, like in the binary erasure channel. And it's summability. So basically it's saying y is the sum of x1 and x2. So if it's the case that y is equal to 0, then we know exactly that x1 and x2 must have both been 0. And if on the other hand y is equal to 1, or sorry, y is equal to 2, then we know that it must have been the case that x1 and x2 were both equal to 1. But in the case that y is equal to 1, we don't know which of two cases it was. It could have been the case that x1 was 0 and x2 was 1, or it could be the case that x1 was 1 and x2 was 0. And we can't distinguish between these two cases, so it's very similar to a binary erasure channel. In that particular case, when we receive a 1, we just have to say, well, sorry, we give up. We don't know what to do. That doesn't mean that you can't communicate, because there's some probability of that happening. I mean, actually, maybe it seems like, I mean, you might think naively, or even sensibly, not so naively, that this is an impossible channel to communicate, because again, x1 and x2 can't coordinate with each other. Right? They can't. You can't say, okay, x1, I mean, if you do this, I'll do that, or something, or there's some statistical relationship between what x1 and x2 do. I mean, unless you're doing TDMA, but again, like I said, that doesn't count. That's not considered officially cheating. That sweeps under the rug, I mean, I don't know, I keep saying this, but it sweeps under the rug all of these technical marvels that are necessary in order to have clocks across great distances that are perfectly synchronized, and to synchronize them to begin with. That itself is a technical problem, an engineering problem. But in any event, the point is that x1 and x2 can't communicate. So how do we do this, or how do we analyze the capacity? So one thing to note is that if x2 is equal to 0, then the rate, then 2's rate is just going to be equal to 0. And we have this perfect open axis channel between x1 and y, and r1's rate is equal to 1. So that point is achievable. We can say, okay, x2, you just don't communicate at all, and I'm going to take the channel. That works, that's a possibility. And then symmetrically, we can do the opposite. Not yet symmetrically. To get the rate of 1, we want x1 to be a Bernoulli. I mean, that's the maximum rate. We're transmitting 1 bit on average per channel. And then here's symmetrically. If we decide to set the rate of R1 to 0, then we can do that by just identically setting x1 to equal to 0. And that opens the channel between x2 and y to allow R2 to be equal to 1. So again, what we've done here is we've achieved these 2 points, this point here and this point here. Now the question is, what happens in between? Now one thing you could do is you could do TDMA, and that would allow you to do this, right? But is that really the constraint? Is that the capacity region? No, not necessarily. In the case before, when we did the binary multiplier channel, we actually had a constraint that R1 plus R2 has to be less than or equal to 1. We don't have any such constraint here. We don't have that. So while this green line, which I drew, is achievable, that doesn't necessarily mean that that's the frontier between achievability and unachievability. It might be. We just don't know yet. We can't just blankly state that that is the frontier unless we have a constraint that says R1 plus R2 is less than or equal to C, some constant. And even that doesn't mean it's the frontier. That might be an outer bound. There might be other constraints which further restrict it when we have such a constraint. R1 plus R2 is less than or equal to some value. All we know is that in this particular case, because we have achieved this upper black dot up here and this lower black dot down there, we know that we can achieve with TDMA any point in between in this line. But that's not, as I said. So let's see if we can then understand this a little bit better. So let's assume that R1 is equal to 1. So R1 is achieving, is at its, in some sense, capacity. So that means that X1 must be Bernoulli. Okay? So X1 in some sense acts like noise for X2, right? So like, think of it as like we've got Y. What am I doing here? Y is equal to X2 plus X1. And this is like noise from the perspective of X2. Now, noise doesn't mean necessarily we can't communicate. So like what we did say is like, okay, well one way of doing this is like X1 you communicate at capacity, and X1 you do nothing, or X2 you do nothing. But we're saying something different. We're saying maybe we can actually allow X2 to send some bits over to Y as well. And in fact, what it does, and this is where the binary eraser channel comes in, it turns the channel from X2 into Y into a binary eraser channel with alpha is equal to 1/2. Okay, why? Because basically, when we have this picture, if X1 is 0, then Y2 has a perfect, Y becomes whatever X2 is. But if X1 is 1, then it sort of potentially erases the symbol. And so therefore what this means is that when X1 is equal to, when X1 is equal to this Bernoulli, this uniform coin flip Bernoulli process, it's still the case that we can communicate using X2 in the same fashion as we can communicate using a binary eraser channel. So any code we have for a binary eraser channel, we can actually use for that, in this case as well. And what is the capacity of such a code? Well, the capacity is going to be 1 minus alpha, and alpha in this particular case is 1/2. So that becomes the capacity of C2. So what we've said is that rate 1 is 1. So we've got this point down here working. And rate 2 is 1/2. And since we can get any point in between, we've got this line here. So it's not necessarily the case that we have to just do this diagonal here. That's not the boundary, in fact. And then symmetrically, we can, at this point, right, which basically says that X2 is equal to full capacity, it's equal to 1. And then X2 becomes noise from the perspective of X1, and then we can do binary eraser channel coding for X1 and achieve this point. That means we can do this. And now that we've got this point here and this point here, we can do simply TDMA to get any point in between. And so the achievable region has this polyhedral structure. So in this particular case, the achievable region is a polytope. Because the convex closure doesn't change it. Like it's already convex, it's already polytope, and so we take the convex closure, nothing changes. So any questions? Yeah.
It seems like if you said that the TDMA argument can be used to show that the region is always convex for, like in general, then I would believe you. But if you said it's not necessarily convex in more general settings.
No, I'm just saying that a TDMA is just an intuitively very easy way of seeing how we can actually, as soon as we have any 2 points, we can take the convex closure between them. So actually, we haven't yet proven that is the convex closure. We're using TDMA as sort of as a crutch, as an intuitive crutch to understand how we can, maybe with a little bit of cheating, maybe not so much cheating, we can achieve the convex combination of any 2 achievable pairs of points. But what we will do is we're going to prove this theorem, which is going to show that there exists a code that can achieve the convex combination of any 2 achievable pairs of points. Now that's the Shannon argument. The typicality Shannon argument will show that there exists a code that can do that. Time division, TDMA is one way of doing it very simply, that time does time sharing. There are other much more sophisticated coding strategies that don't require a synchronous clock. That can do that as well. And again, what we're interested in is this theoretical problem of what's the achievable region? What's the point? Where is it the case? What points can we show that there exists a sequence of code such that as the block length goes to 0? That doesn't even necessarily mean that we can actually find that code or that in practice. It just means that there exists a code using typicality theory. The same the way that we showed the existence of a code in the point-to-point communication case. Okay.
So you kind of hinted that there might not be a convex region.
There. What I was saying. Well, first of all, we're studying the MAC right now, right? So in the MAC case, it's convex closure. We had that theorem that in the MAC case, it's convex closure. In this most general case, when we're in R to the m squared dimensions, when we have crazy codes, we don't know. We need to study individual cases first. And this is our first instance of network information theory where we have a simple setting, the MAC setting. But we will be studying, next week more instances. And like I said, we're not going to be able to touch on a lot of cases that are well studied. We're going to study some simple ones, and just at some point next week we're going to start saying, yeah, this guy can do this guy can do this, that guy can do this. But this is one that's well studied, and this is one that's important because this is one that's fully characterized. There are many settings where it's still not most general, and we still can't characterize the frontier. Meaning there's no theorem that says this is what the frontier looks like. In the MAC case, we have a theorem that says this is what the frontier looks like. We have a mathematical way of describing precisely this frontier. And now now not only are we in the MAC case, we're in the binary erasure MAC case. And in the binary erasure MAC case, it happens to be a polytope. That doesn't violate the theorem, it's just we're in a further specialization of the MAC, the binary erasure MAC. If we generalize to MAC, we've got the convex closure theorem that we still need to prove. And if we generalize further to non-MAC channels, like I said, it's still a unknown territory. I was looking for Old West terminology there. I couldn't find any. It's the Old West. And there are little, everyone in here is a gunslinging information theorist. Nobody gets that. Has everybody seen a Western movie? Does anyone like Westerns?
It's hard to imagine a guy singing information.
I know, that's why it's an ironic joke. This is called irony. So that's why it's a joke. I can't imagine a gunslinging scientist, for that matter. Anybody is. Actually, I think there must be. There must be something. My weapon is my iPad. pen is mightier than the sword, and the iPad is mightier than the pen. So here's the theorem that we want to prove again. This is the general case of the general math capacity. This is the theorem that we outlined before, and we spent some time understanding it and how it generalizes the one-dimensional case. Important to realize that it's still a Mac, and what does this convex hull mean? So here's kind of what we really mean. This is the general case. So we have all of these polytopes, and let's zoom in a little bit on this. So here's one polytope, like this guy. And here's another polytope. There's another polytope. These are all polytopes, but we're taking the convex hull of all points in any of them. So what we need to be able to show is, for example, if this point here, this pair of rates and this pair of rates is achievable, then in fact we can do everything in between, even when you can see in this particular case it leaves the two polytopes. So does the intuition make sense? So we have an achievable point in one polytope and an achievable point in another polytope, but the theorem is saying that we can take a convex combination of those achievable points. We leave the two polytopes, and that's still achievable. It doesn't say that it's easy to get such a code. Right, so it's convex closure of all R1 satisfying these three things. Is that clear to everybody what we're saying? Sometimes it's a little bit tricky to even just understand the theorem. Raise your hand if this is dead clear. Raise your hand if it's critical condition clear.
It's just been shot by a
gun wielding information theorist? Yes. Raise your hand if it's serious. Raise your hand if it's just flu clear.
Question.
Yes, good.
So each region is for a specific family of that joint distribution, even that they're independent. Because each product distribution gives you a specific expression for each of those mutual information terms that we have, right?
Yes, each product distribution gives you specific constraints on the R's, on the rings.
Once you fix that product distribution, those upper bounds are fixed. You get one of those solutions. Once you change the family of the product distribution, then you get another one, right?
That's right. That's right. And that's what these, when we zooming in on here again. So we have these two polytopes, like this one and this one. Right? And each one of those product distributions are saying that each one of those are possible. Right? But then what the convex closure is saying is well, if I take these two blue points, zoom in a little bit more, you've got this blue point here and this blue point here, then I can take a convex combination of them, and that's still achievable. Even though it's the case that we leave, this little bit here leaves the two polytopes. That's still achievable. That's what we mean. And then when we take the convex closure over all of them, it kind of looks, like this bit. That's kind of what's going on.
And one more thing. So here we assume that all users are communicating at a single frequency, right? Otherwise, if it's OFT, another multiple access scheme, so.
Yeah, you're talking about FDMA, frequency division. Those are also ways of achieving it. We haven't really talked about the Gaussian MAC. We're going to be doing that maybe today, maybe on Monday, but definitely one can achieve ease of coding constraints when one does frequency division multiple access. Let's look at, for example, radio transmissions. Everybody's got their own little slot, and essentially it's the same channel, and we do FDMA all the time. But there's also things like spread spectrum and other coding strategies, which I guess arguably couldn't be seen as FDMA. It's everybody's spread out all over the place. So that's and then there's a lot more sophisticated methods as well. There's a whole world of wireless communication coding strategies where you take this, the radio spectrum and you carve it up either in frequency or in time or somewhere else, in basis function. It gets very sophisticated. I mean, it's amazing. And we use these things, or, do you do wireless research?
Yes.
Yes, you probably know about this better than I do. So, but the point is that there are different strategies within which one can take a channel and carve it up into different regions. And FDMA and TDMA are only very simple instances of that. But it's much more sophisticated than that. What we're talking about here is the existence of codes, right? So as soon as we got the existence of codes, so we can prove the existence. As soon as we know that it exists, then we can start searching for it. That's what. So we're looking at the mathematical aspects of it. And so, like, the thing is, if we can prove that it doesn't exist, you're not going to expect to see a rate pair that is outside the achievable region. So if your boss says, "Why haven't you achieved, 3.6 bits, 4.8 bits?" and you say, "Well, because it's not achievable. It's not under any condition." Assuming your model of the channel is correct. And these are all based on models of the channel. So you, of course, also have, when you're doing this in real world, need to have a good model of the channel. So, and you can measure that. That turns into a machine learning problem. How do you do density estimation or statistical estimation problem? That's why everything needs machine learning. So, okay, so let's prove at least the first part of this theorem, the achievability theorem. That basically, the achievability says that if it's the case that we've got a pair of rates, R1 and R2, that are such that it satisfies these inequalities, the inequalities that we stated, and here they are again, right there in the theorem, and it's the case that it satisfies them for some product distribution, P of x1 and P of x2. So it has to be one of them. As long as there's one, then we're happy. Then it's the case that there exists a code such that the probability of error goes to 0. Okay, so this theorem, the proof of this theorem is going to mimic, again, the Shannon theorem. So again, we've seen this form of theorem a number of times, so I'm not going to go through it that quickly, or I'm not going to go through it that slowly, or that, I should say, I'm not going to go through it that carefully. But we are going to go through it. Okay, so first of all, what we do is we generate independent code words, like we did in Shannon. In this particular case, we need to generate 2 to the nrk independent code words for k is equal to 1 and 2. Right? Because we need code words for x1 and code words for x2. We've got a rate R1, we've got a rate R2. We've got n channel uses in both cases, and so therefore we generate for each possible message that we want to send, for I is from 1 to 2 to the nrk, we need essentially a string of x symbols of length n that acts as the code word for that message I. And so that's what we're doing here. Okay. And we're doing it independently. Now, again, why do we care about independence? Why do we do that? Well, the symmetrization argument of Shannon's is going to allow us to assume the index 1. And all the other ones are going to be independent, which allows these nice theorems about independence and typicality to be used to show that the errors are going to be bounded above and are, in fact, going to be going to 0 exponentially fast. So the code words are known correspondingly to the senders and the receiver. If you're sender k and you want to send message I, then you send this. So this is a string of n input channel symbols for k. K is equal to 1 or 2. And so how do we decode? And we're again doing typical set decoding. So we've got a string of output symbols. We've got y. We've got this bit, right? And then we say, okay, well, let's choose a pair of indices, I and j, such that the code word for I and the code word for j and the received symbol y is jointly typical. And that's how I get my I and j. So that's what you guys said. That's what x1 and x2 said. And either you get the right answer or you get some error. And what we want to do is show that the error goes to 0. Now, the other thing to note is that, in this existence proof of a code, we're not using TDMA. Right? So there's nothing about TDMA that's being used here. There's no time division. There's no specific frequency division or any sort of specific coding strategy. So this is very general. And so we do the random code construction. And so again, by symmetry, this is Shannon's amazing argument that we can, when we sum over all things and we take the expected value over all possible code books, the sort of actual code words don't matter. Right? So what we can do is like we did before, we swap out the sum and take the average, and what only matters is that we can just say, let's assume without loss of generality that index 1, comma 1 was sent, and then bound that error. And when that error is bound, then all of the errors are bound. Because again, it's the symmetry of the code words. This is the random code word construction. So we're going to assume that ij is equal to 1, 1. And then we have these possible events. So Eij is just an indicator, it's just of an event that happened. So Eij says that, okay, so we received y, and it's the event that the code word for I and the code word for j and the received sequence y is jointly typical under the case that we were sent that index ij is equal to 1, 1. Okay, so what you can expect is going to happen is that the only thing that's going to have any probability is E11. Right? Meaning that the code word for 1 and the code word for 1, the code word for 1, this code word for 1 for input 1 and this code word for message 1 for input 2 is going to be jointly typical with the received singulets, and anything else is going to go to 0. So what could possibly be anything else? Well, it could be the case that those code words that we chose are not jointly typical, right? That's a possibility because, again, for any finite n, we might not have joint typicality. Of course, that's going to go to 0 very fast. But then the other ones are going to be that some other code word which was drawn independently, like message number 3 is jointly typical with y for 1 or 2 of the inputs. But that's where we use this probability that says, oh, well, wait a second, if these guys are conditionally independent, given y, then that stuff has this probability to the negative n mutual information. And that's going to go to 0 as long as the mutual information is greater than 0. So here's that probability. So the probability of error is that first instance is the complement of the joint typicality with 1, 1, which is the probability of the atypical set. And then we take the union over all indices that are not both 1, 1, and we look at that event. And then the union bound, all we need to do is show that an upper bound of that probability is going to go to 0. And so we're going to break apart these events into the union of these individual events, which is an upper bound, but if we can show that each one of these terms goes to 0, we're done. So here are the different terms. The first term is the atypicality case. The second one was when j is equal to 1 and I is not. The third is when I is equal to 1 and j is not. And the fourth is when both I and j are not equal to 1. So the first one is going to go to 0 by joint typicality, which we know. And then we're going to bound this one. We bound this one, and by symmetry we're going to get the other one. So what does this mean? Let's see, does it help to zoom in a little bit on this? A little bit. Okay, let's go through this. So the first bit is to say, okay, the probability of this error is to say that, okay, I've received y. This was sent, so in other words, message 1 for input 2 was sent, but the code word for message I, where I again is not equal to 1, happens to be such that those three code words are together jointly typical. So what's the probability of that actually happening? So again, remember that these were drawn independently, right? So x1, x2, and y were drawn independently. So we use the independent code word construction. So that means that is exactly the same as that these independent events, so this is independent of this, are jointly typical. So that's going to be the sum over all of these pairs in the joint typical set, but then we take the product distribution, because remember, it's an independent event. So I can use this in different colors. Okay, so now we start using these typicality set bounds, which, like I said, if you don't remember them exactly, just go back and look at the theorem. But the first is like the number of terms in the sum is upper bounded by the size of the typical set. And then we have these two different probabilities. Each of the probabilities are basically equal to 2 to the negative h of the corresponding events. So we've got 2 to the negative h of x, 2 to the negative n h of x1, x2. The first one is negative h of x1. The second one is 2 to the negative n h of x2, x, and y. x2 comma y. So we combine all this stuff together. The epsilons combine. We're also using the upper bound on the size of the typical set, which goes into this bit here, right? 2 to the sorry, that's wrong, but it goes into this bit here. It's 2 to the h of x1, x2, and y. That's the size, the upper bound on the size of the typical set. So the negative is used twice. And that, when we combine terms, just gives us the mutual information. And then since x1 is independent of x2, we use the chain rule of mutual information to say that that's exactly equal to this bit here. Right? So it's basically saying this mutual information here is equal to the mutual information between x1 and x2 plus the mutual information between x1 and y given x2. But the mutual information between x1 and x2 is equal to 0 thanks to this property here. And so therefore we get this last bit here. Okay, questions? So we've got that bound. We can use exactly the same procedure to show this bound, and an exactly analogous procedure to show this bound. You know, the epsilons don't matter whether it's 3 or 4 epsilon. That basically just corresponds to how many terms there are in the sum, right? So those are finite and fixed, and they don't change as a function of n. Those are constants, and so those don't matter. And so what we end up getting is that this whole thing goes to 0. As long as it's the case, and that was the assumption that we made, that the rates are strictly less than the corresponding mutual information terms, because then the powers are such that it's negative n times a positive value. So again, we're not saying precisely what happens at the boundary, because again, that what actually happens there depends on a very special case, which we can analyze, but we're saying whenever it's the case that the rates are strictly less than those values. So that basically means that there exists a code that achieves those rates. Any questions? Okay, let's talk a little bit about this thing. So now remember, we've got the chain rule of mutual information again. And let's look at, again, the picture to get a little bit more intuition. It's nice to intersperse intuition. So why do we have these extreme points on the polytope? So obviously, you know, we're not going to have any negative rates, right? So we're going to have that. So why do we have this, 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 and this? Why are those sensible? In particular, the ones we haven't really looked at is like, why are these labeled? Why are these labeled the mutual information? So, if for example, like x2 communicates at a rate of this mutual information here, and then x1 communicates at this rate here, then when we sum up those two rates, we're exactly going to get that. Right? So in some sense, it's impossible for, in order to achieve this, the bound on the sum of the rates here, and if this guy communicates at this rate, it's impossible for x2 to communicate at a rate greater than that. Why? Because if it did, we would violate the R1 plus R2 constraint involving this quantity here. So that means that the shape of the polytope must have this basic form. I mean, it could be a triangle, or it could be a square, or it could be anything in between. So here's a way of doing it. Like, for example, a decoder might say, the typical set decoding strategy would say, first decode W2, and do typical individual pairwise typicality set decoding for just x2 and y, which says find me a typical code word, typical x2, comma y code word for x2. And then once I'm done with that, sort of fix on that. So okay, I'm done. But now what I want to do is find a corresponding typical x1 where we're jointly typical here. So that would, for example, achieve. You tell me which point would that achieve? That strategy.
So first you're decoding.
First we're decoding x2. So first we're doing this bit here. And then we're doing this bit here. This becomes 1, this becomes 2. No, sorry, that's step 1 and step 2. So what point on this polytope are we achieving by doing that?
So you get the most.
One on the axis.
We get this one?
Yes.
No. Look at that one, because remember, both guys are communicating at some rate. That would mean that x1 is communicating at rate 0.
You're treating the other one as noise, right? Because the interference plus noise, right?
We're treating the other one as noise, but that doesn't mean that we're computing at a rate 0. We saw an example, in fact, of the binary Erasure channel where that doesn't imply that you have 0 rate for the other one.
But whatever one you decode first, you get the maximum rate on that for that guy. Right?
And what's that?
So that's if you decode x2 first, then that puts you as far up as you can go.
Which isn't that I of x2y, x2y.
You already have maximum rate for x2, and then whatever you can get left for x1.
Yeah, so what would that do?
That's on the top, the first spend of the pentagon there at the top.
So you get this one.
Pentagon there at the top.
Now, the converse of the theorem, states that if we do have a sequence of such codes whose probability goes to 0 and then goes to infinity, then it must be the case that the two rates are within this convex hull of all of these polytopes. Right? So now here is basically saying, okay, well, you know, this is the thing that sort of achieves this convex region. This is where we need to sort of come up with a clever argument that says that you know, we're not reliant upon any particular polytope, but we can achieve any one of these polytopes somewhere in there. Okay, so what do we do? Let's look at the way in which the code gives us this joint probability distribution over all of these random variables involved. W's, which are the original messages, W1, W2. The X's, which are the code words, and the Y's. Remembering, of course, that given the messages, the code words are deterministic. Right? So once we've got a message, we choose the code word. And once we've chosen the code book, that might be a random strategy like we did in the proof of the primary theorem. But we have a uniform distribution and independent messages. So the first part is 2 to the negative n r1 plus r2. Then we have these conditional distributions, which chooses code words for each one of the W's. And then lastly, we have the channel. And that's the joint distribution over all of these guys. Now remember Fano's inequality? Fano's inequality lives. Many of these things involve this. Maybe, okay, well here's Fano's inequality. We're out of time again. And I was hoping to do more, I guess, does it seem like I'm going too slow? Raise your hand if you think I'm going too slow. Raise your hand if I'm going too fast. Okay, I was hoping to finish all of this stuff today, but somehow it managed to become 20 after again. Anyway, we'll start again this on Monday. We'll start this again on Monday. Please watch the YouTube lecture again, because we're sort of in the middle of this discussion, so that we can just start right off. Maybe I can do a minimal amount of review on Monday, under the assumption that you've seen all of this stuff again. Okay. All right. Any questions? Any last questions?
So this typical decoding is ML decoding basically, because you're trying to find the pair of, let's say, messages that are like high probability.
Do you mean like ML, like maximal?
Yes.
Likelihood? You remember, I mean, we sort of enumerate, I mean, in theory, we would enumerate the typical set. So it's not even necessarily like finding the most probable one. It's just sort of, once the block lengths get big, we just, for every possible coder, we have a typical, we just have a big giant table. Now that's not practical, of course, but it is ML decoding in the sense that it's the most likely code word, but it's the only one, right? Because when the block lengths are big, everything else is, the probability of all the other ones sometimes is 0.
We enumerate all possibilities.
Yes, at least in theory, yeah. But we would not, this is not a practical coding strategy. Okay.